There we go. I have to say, yes, I accept recording. Lovely. Right. So welcome to this talk. I'm Steve. I'm very easy to find on the internet. And I work for ThoughtWorks, which is a lovely global technology consultancy. So if you ever want to work with a lot of very lovely, clever people, come say hi. And the title of this talk today is Building a Culture from Chaos. We're going to be talking about a couple of things, and we will get to what I mean by building a culture, that part of the talk, in just a sec. But the chaos part here refers to chaos engineering. Maybe a show of hands. I think you can either use the Zoom reactions, or you can put your answer in the chat, and I should be able to see that, hopefully. Who here, there we go. Thank you, Vladislav. I can see you've got a thumbs up there. Who here has ever done chaos engineering? Hands up if you have. Got a few. Okay. So there are a few emoji around. There are a few reactions from earlier, so I'm not sure how many, but certainly not a lot of people, it looks like, right? So I think it's always worth kind of introducing chaos engineering because while it's been around for many, many years, it's not exactly mainstream. It's not exactly something which every single company is doing, but I do think it's something that is a really powerful and effective technique. So to introduce chaos engineering, I usually start with the story of how chaos engineering came to be, how it started. And like a lot of stories in our industry, this story starts around 2010 in Netflix. So around this time, Netflix was involved in what we today would call a cloud transition. They were moving from their own data centers. They had their own buildings filled with all their own machines, and they were moving to the public cloud, AWS specifically. And as they were doing this, they decided not to do just a lift and shift, right? Where they take all of their old systems, move them onto the new cloud and call it a day. They decided to actually re-architect how they were doing things. And what they did is they started taking their big services that handled all of their business and started breaking them up into smaller services. Again, they were doing what we today would call a microservices transition. This is something I've done now several times in my career. This is a fairly well understood pattern in our industry. And as they did this, they realized something very, very important. They realized that if they did this wrong, they didn't put a good amount of thought into how they approached this, they would actually make the situation a lot worse. They had reliability issues at Netflix. There was an incident at one point which I believe took down pretty much their entire business for several days, including the system that delivered the DVDs. Remember when Netflix used to deliver physical DVDs? And they realized that if they split up these big services into lots of microservices, they can actually make the system even more unreliable. Although we often kind of associate microservices and these sorts of things with scalability and resilience, you don't get that for free. And if you go from one service, which runs your entire business, to thousands of services that run your entire business, and any one of those services going down causes your entire business to fail, you've just created thousands of single points of failure, which isn't great for reliability. There's thousands of things that can go wrong that can bring down your business. So to avoid this, Netflix put together what they called the Netflix engineering principles. Now, full disclosure, I've never worked for Netflix. But I do know people who have, and they've told me that these were actually printed out on the wall. These were hung up on the wall of every office so everyone could see them. And the first of these engineering principles was that there should be no single points of failure. So any service should be able to fail, and the business as a whole keeps running. There can be slight service degradation, You know, if the recommendation service goes down completely, maybe you lose your recommendations, but you should still be able to do other stuff on the site. So no service should be a single point of failure. And this was such an important concept for them, such an important principle, that the second principle they followed was to never, ever trust that they got the first principle right. And this is a great thing to write on a sign, put it on a wall and say, these are our engineering principles. But they actually built a tool to do this second one. They actually built a tool to constantly validate whether or not they had built a system without single points of failure. And that tool is Chaos Monkey. If you've heard of chaos engineering, you've probably heard of Chaos Monkey. What Chaos Monkey does when they turn it on, when they activate Chaos Monkey, is that it starts attacking random servers. It looks at all of Netflix's services, their servers, and it just starts turning random servers off. And it does this to test that hypothesis. Did they build a system with 0 points of failure? Because if they did, Netflix should keep running. You should keep being able to watch whatever it is you watch on Netflix. So they're constantly validating their assumption. They're constantly applying principle number 2. They don't do this 24/7. They only do this when there are Netflix engineers in the office. So if something does go badly wrong, they can step in and fix things. But this is a way of taking this from a principle that's written on a wall to something that they actually do every day. And they didn't stop at Chaos Monkey. They built Chaos Monkey's big brothers. This is Chaos Gorilla and Chaos Kong. They do the same basic thing, but at a bigger scale. So Chaos Gorilla takes down entire data centers, and Chaos Kong simulates the failure of entire regions of Netflix. So again, what they're testing here is if an asteroid hits the west coast of the US, people should still be able to watch Orange is the New Black, right? That's absolutely critical infrastructure in a post-apocalyptic world. And these are the kind of, the big ticket, the big poster, monkey-based tools that Netflix built. But they built loads of others as well. One of my favorites is Latency Monkey. So what Latency Monkey does is it simulates latency. It simulates just little delays in the network. So a network request that used to take 200 milliseconds, well, now it takes 2000 milliseconds or 2 minutes even. And if you think about it, this is exactly the kind of failure that happens in the real world. Network switches overheat. Someone is walking through a data center and they trip over a Cat5 cable. This stuff happens, and what Latency Monkey is testing, what Latency Monkey is validating, is whether or not they've built a system that is resilient to those sorts of failures. And they built a whole suite of monkey-based tools that they call the Simian Army. Just for a small little bit of context here, this is from a previous era of the internet, where internet-based monkeys were good and cool and not all just scams. But the work Netflix did here, not just building the tools, but also publishing them, making these freely available to anyone on the internet, and talking about these approaches really helped chaos engineering take off in a lot of spaces. If you want to get started with chaos engineering, I actually don't recommend you get started with a Simian Army. They're very mature, powerful tools, yes, but they're also, they also have some dependencies on some fairly Netflix-specific build infrastructure like Spinnaker. And if you're not using Spinnaker, it's a little bit of a pain to get them working. In the past, I've used Chaos Lambda, which is an extremely simple little tool. You literally tell it which auto-scaling groups to attack, and it will just start attacking them and start taking them down. By default, it starts off, so it starts harmless, and then you just get to kind of configure it in the specific way that makes sense for you. Again, full disclosure, while I've used this before, I did check, and this hasn't been updated since 2018. So it probably still works because it's a very, very simple tool and a very, very powerful tool. There's also tools like Gremlin, which I think pitches itself as chaos as a service, a way of targeting particular servers and trying to see if you can survive their failure. I think Netflix did a lot of good work here, kind of publishing and talking about these tools and these techniques, which led to the growth of these sorts of approaches. And after a while, they kind of looked back on everything that had been made, and they realized that they had invented something. They realized that they had invented chaos engineering. And they put together principlesofchaos.org, which you can go to. And they put together a description of what chaos engineering actually is. And they said that chaos engineering is the discipline of experimenting on a system in order to build confidence about the system's capability to withstand turbulent conditions in production. I like this description for a couple of reasons. First is it calls out it's a discipline. Very often when we talk about chaos engineering, and I'm guilty of this as well, I did it a few minutes ago, we talk about it like Netflix just releases the monkeys and they start randomly destroying servers. But it really isn't that simple. There is a discipline to designing and running chaos experiments that's really important to actually getting value out of this approach. I also like that it calls out that it's about experimenting. This is an experimental approach. Netflix have a hypothesis that they have built a system with 0 points of failure. Chaos engineering, Chaos Monkey, is testing that hypothesis. They're running experiments to test their hypothesis. This is a disciplined, scientific, experimental approach. I also really like the fact that it calls out that it's about increasing our confidence in the system's ability to withstand turbulent conditions in production. Because the kind of failures that Chaos Monkey and the various chaos tools are simulating here are the kind of failures that we see in the real world. No matter how perfect your code is, it's running on a server somewhere. Even if you are working with public cloud, you're working with AWS, GCP, .NET, Azure. So I had to think for what the Microsoft one was for a second. Even if you just press a button and a server magically appears for you, there's still a physical server under there, and physical servers fail. No matter how good your code is, something else in the chain can still fail. And I like chaos engineering because it's honest about that. I sometimes describe chaos engineering as an honest approach to engineering. It acknowledges that, yeah, this stuff happens. We should be ready for it rather than just pretending it doesn't happen. I like this description, but I always sort of think about chaos engineering at its core is about running those chaos experiments, right? We sometimes call these times when we release the chaos monkey, when we start turning off servers, as experiments. All right, so that's when we release the monkeys. We sometimes even call the tools chaos variables. We are injecting a chaos variable into a system. And we keep doing this until something fails. And then we learn from that failure. We use this as an opportunity to learn about where are the limits of our system, what went wrong, what went right. We use this as an opportunity for learning. I highly recommend the work by John Allspore, Sidney Decker, Todd Conklin, looking at how we actually learn from failures. I will have a big page of references at the end, so you don't need to take too many screenshots or anything right now. But the ETSI debriefing facilitation guide really looks into how we learn from these failures, not just how we fix them, but how we learn from them. And once we've learned from the failure, once we've understood the limits of our systems, where they work and where they don't work, then what we do is we improve the system's resilience. This word resilience here is important, right? Resilience is distinct from robustness. Robustness means something is unlikely to break. Resilience means it can withstand being broken. It can keep going after it's been broken. Some people would kind of frame this as fixing bugs. I probably wouldn't, but that's more of a philosophical point. But ultimately, this is the loop of chaos engineering. This is the core loop of what do we mean when we say chaos engineering. We are running chaos experiments, we're causing failures, we're learning from those failures, and then we're improving those systems so the failures don't hurt us in the same way again. So now you're all chaos engineering experts. I have a little bit of an admission, because this talk, while it's nominally about chaos engineering, what I really want to talk about today is complex systems. So I'll ask another question for the audience. So again, you can use your reactions, or you can put it in the chat. Who here would say that they work in a complex system? Give me a second to answer. See if we get any thumbs up. I've got a few thumbs up there. There's a couple of people. Yep. Okay. So there's some people saying yes to that. And when I ask this this question in front of kind of technical audiences, fairly commonly, I do see a lot of people putting their hands up. People seem to say, yes, we work in a complex system. What's interesting is I haven't actually defined what a complex system is yet. And yet some people went right ahead and put their thumbs up. So that's good. That's bold. I like that. But this term complex system actually does have a very technical meaning. There is an entire field of study, the study of complex adaptive systems, devoted to understanding complex dynamic systems. And we can think about them in a couple of different ways. So one way we can think about complex systems is in how they look. One property of complex systems is that they have multiplicity. What we mean by this is there's lots of stuff in them. There's lots of elements, lots of moving parts, right? If you've heard this phrase, lots of moving parts, maybe that's a sign that you could potentially be looking at a complex system. But as Paul Cilliers puts it, you know, if you're walking on the beach, you've got you've got sand everywhere. Well, obviously, there's lots of moving parts there as well, but is that really what we're thinking of when we say complex system? Maybe not. So we need something else. We also need a high degree of interdependence. So we need lots of communication links between those elements. So if we think about a crowd now, a crowd of people, a group of people like yourselves, for example, you can all talk to each other. You can share information with each other. And those interactions can be non-linear. What that means is a very small input can lead to a very large output. If you start a rumor, that's a very small input of energy, but very big things can come out of that. And another thing, another thing that we see with complex systems is that they also have a high degree of diversity. So not every element is the same, but every element is different, or there's a high degree of diversity among the elements, which of course means there's a high degree of diversity among the connections between them, the communication links. Think, you probably have a different relationship with your work colleagues than you do with your family. It's not that one is better or worse, well, maybe, but there's a high degree of diversity in both the elements and the connections between them. And this is a good start, but I don't really think that this is enough. Understanding these connections between them, the interactions between these elements, is absolutely critical, but it's not really enough. And I think it's more helpful to think about complex adaptive systems in terms of their behavior. What do they do? How do they interact with the world? One of the properties or one of the behaviors of complex adaptive systems is that observers, oops, oh, sorry, I messed up a slide transition there. I think sometimes when I ask this in front of technical audiences, lots of people say, yes, I work in a complex system, because we find ourselves looking at architecture diagrams that look just like this. We see, there's lots of interacting parts, lots of non-linear interactions. This feels complex. This feels different from just, putting together a chair or something. But again, I think it's more important to think about the behaviors of complex systems. One thing in complex systems we need to take into account is that observers change the system. If you've ever gotten stage fright, you'll understand what this is like, right? It's a very different experience to be speaking in front of your bathroom mirror and speaking in front of a huge crowd of people, because observers change the system. They become a part of the system. I'm lucky I don't get stage fright, but I was pairing with a colleague a few days ago, and I misspelt my own name 6 times in a row because observers change the system. They become a part of the system, and the system adapts to the observers. This is key. Every time we interact with the system, it reacts, it adapts, and it changes. And this sounds kind of basic on the first level, right? Hey, systems change over time. Yes, anyone who has a gray hair will understand this. But there's some more subtle things here. What this means is an approach, a plan, a technique, something that worked yesterday might not work today. So if you've ever, so maybe think about where you were for the first wave of COVID. I actually started in India, but I spent most of the first wave of COVID here, where I currently live in Berlin. And the first lockdown was pretty harsh. The first lockdown was pretty extreme, and it was like nothing that anyone had ever experienced before. Shops were shut, everything was shut. We couldn't do things that we just thought of as normal for our entire lives. But ultimately, we got through that. It was a difficult time, but we kind of felt we were all in this together, and we made it through. Now, if the government, wherever you are, if the government announced the exact same lockdown measures that they announced in March 2020, if they announced those exact same measures tomorrow, would they have the same effect? I'm assuming probably not. As the Greek philosopher Heraclitus has put it, you can never step in the same river twice. Every time you interact with the system changes, it adapts, and it evolves alongside you. The implication here is that when we're interacting with complex systems, we need to co-evolve with them. If we just have our plan, we follow our plan, and we ignore the rest of the system, we're going to be left behind, because systems adapt. And because systems have all of these complex adaptive systems have all of these interacting elements, all of this unpredictability, all of this adaptation, we have unintended consequences. As Barry Commoner put it, the first law of ecology is that in a complex system, or in an ecology, you never just change one thing. No matter how carefully you plan, there will always be unintended consequences. If the image on the screen behind the text looks familiar to you, it's because it's an image known as the blue marble. It was taken by the crew of Apollo 17 on their way to the moon, and it's one of the most widely distributed images in human history. The crew of Apollo 17, all of their observations, all of their scientific activities were carefully timed. There's a very, very strict timeline for these missions. But this was actually an unplanned photo. The crew had a few moments to spare. They floated over to the window and they snapped this picture of the Earth as it receded away from them. A couple of years later, there was a campaign to release these images, make them public domain so everyone could see them, everyone could use them. And NASA did that. They published these images. And for the first time in human history, the whole Earth could see the whole Earth. They were able to look down and not see borders and people and countries. They were able to see a fragile oasis hanging in the darkness of space. This image is credited with creating the environmental movement as we understand it today. It shaped generations of environmentalists. Could you have predicted that when the astronauts of Apollo 17 floated over to the window and took that picture? Probably not. And if we went back in time and we took the same picture again, could we guarantee that the exact same environmental movement would come out again? No, we couldn't have. Because when we're in a complex system, we never just change one thing. There are always unintended consequences. These aren't rare occurrences. These are the norm in complex adaptive systems. And there's lots more that we can talk about with complex adaptive systems. Complex adaptive systems are self-organizing. They pattern match and they seek patterns and they replicate patterns. They're dispositional, not predictive, which means we can't make these deterministic statements. If X, then Y. But we can say, well, the system is disposed. It's likely to go in these two directions, but we're not sure which. We might also think about these as attractors. There are certain possibilities that are more likely, certain possibilities that we're going to be drawn towards, but it's never a deterministic predictive certainty. We'd say that complex adaptive systems are entangled with each other. It's very difficult to draw the boundaries of a complex adaptive system. Your health is entangled with the health of the people around you. It doesn't make sense to say that your health is the same as the people around you, but it is correct to say that your health is entangled with the entire community around you. Complex systems also have path dependence. What is possible today depends on what happened yesterday. I'm a big test automation fan. I love helping teams get better at test automation and doing all sorts of miscellaneous QA jobs. I'm a QA consultant, hey. But if I join a team and they've just had a big program to try and get them to do more automated testing and they really, really struggled with it and they found it very, very stressful, you know what? While I'll constantly tell you that automated testing is a great idea, now might not be the right time. Because history matters with complex systems. Complex systems, teams, crowds, societies, people have memories. They are path dependent. And I could happily talk about these for days, and I've got lots of references at the end if you want to kind of dig deeper on this subject. But one thing is very, very clear when we're thinking about complex adaptive systems, and that is that we need new approaches for complex systems. Our old approaches are really not going to work. They are fundamentally different beasts to what we might deal with on a day-to-day basis, just like walking around our apartment. One thing I find very interesting is that when I look at the, what for lack of a better term, I will call the Agile community, I see a lot of those approaches. I see a lot of approaches which are relevant for complex systems. Maybe you've heard of big modeling upfront, or big requirements upfront, or big design upfront. Maybe you've heard of this, right? It's a commonly discussed in agile communities, agile circles. It's this idea of before we write any code, before we build anything, we think very, very carefully about the requirements. We do all of the modeling, all of the planning, all of the design that we can possibly do upfront. Right? Measure twice, cut once is maybe another way of putting this. And in the context of the Agile community, and in particular the extreme programming community, which I'm a big fan of, this is often framed as an anti-pattern. It's often seen as not the best approach, to be honest. Because when we're working with complex systems, they change around us. They evolve around us. And no matter how good our planning is, there will always be unintended consequences. There will always be things that go wrong that we could not have predicted. The system will evolve around us. And if all we do is blindly follow our plan, we will fail. So this is an approach here. This kind of rhetoric, this kind of idea and principle makes sense when we're dealing with complex systems. Even the Agile Manifesto, one of my favorite manifestos, has this line here about the importance of responding to change over following a plan. It's not that following a plan is bad. Like, yeah, you probably should have a plan to a degree. An amount of structure is very important. But ultimately, when we're working with complex systems, like a market, like our users, like organizations, things will go wrong. We'll put something in front of people and they'll realize they want something different. The faster horses problem. If I asked people what they would have wanted, they would have said faster horses, and we never would have gotten cars. Well, cars are a bit iffy, but it's another topic. So it's important that we are able to respond to changes, not just follow a plan. And these are, I think, kind of subtly acknowledge the realities of complex systems. There is a book I like, Edge, Value-Driven Digital Transformation. Full disclosure, this is written by 3 of my colleagues at ThoughtWorks. I'm not getting paid anything extra to talk about this. I do genuinely think it's a good book. And it's a book about how to run a business in a complex system, in a complex environment. And they're very explicit about the references to complexity theory. They say that the title Edge comes from the concept of the edge of chaos in complex adaptive systems theory. They talk about how in times of uncertainty in complex systems, our traditional reliance on planning simply won't work. It's not that we don't plan, we do, we just don't believe our plans will survive reality. We need a fundamentally different approach to problems when we are working with complex systems. This is a key point here. You don't need to read this whole book. I do think it's a good book and worth a read. You don't need to read this whole book. It's filled with kind of advice like this and how to run a business in a complex environment. But honestly, simple, pithy little statements like this. We accept failure, right? Has anyone seen this on a wall somewhere? We accept failure. We embrace failure. If you've read the very good book, Accelerate, the science of lean software and DevOps, good book, worth a read, references the Western culture model. The Western culture model looks at how high-performing organizations embrace failure as an opportunity for learning. They see it as an opportunity to get better, not just shoot the messenger. I've seen this so often. I've actually literally seen this framed on a wall in multiple offices from multiple companies that I've worked with and for. And I was talking to Dave Snowden it was last year, I think, about this. And he says that whenever you see this sign, whenever you see a sign that says, we accept failure, what you are actually observing is a process of Darwinian selection to root out the fatally naive, right? So we put up this sign saying, admit when you made a mistake. Let's see who's dumb enough to actually do that. And I don't entirely agree with him here. I think it is entirely possible to genuinely embrace and accept failure. But I think that is a real risk. There's a risk that we say we accept failure, we embrace failure, failure is acceptable, we learn from it, but we don't actually change. We say we accept failure, we have a big sign on the wall, and anytime something goes wrong, people get fired and people get shouted at and people get get punished. A little while ago, I was talking with a client and talking about some of the changes that we wanted to make in their organization. And they, at the end of our conversation, they said, "That's great. I completely agree with everything you just said. Those are amazing ideas. But how do we make that part of our culture?" And I like this question. I thought this was a great question, right? Because it's not just how do we, it would be so easy to take everything I just said, everything we all agreed on, print it out on a big sign and say, these are our new principles. These are our new ways of working. He asked a good question. He said, how do we actually build this into our culture? So it isn't just something we say, it's something we do. Now, changing culture is a complex problem as it happens. There are patterns, certainly. There's replicability in places. But there's a perspective I like from this guy. This is Aristotle, by the way. Aristotle was talking about what it means to be a good person, Nicomachean Ethics. And he said, we are what we repeatedly do. Excellence, then, is not an act, but a habit. Full disclosure, that wasn't actually Aristotle. It was a later philosopher, Will Durant, paraphrasing Aristotle. It's been very important to quote your references. But I like this quote, right? I like this sentiment. We are what we repeatedly do. Being good isn't just something you do once. It isn't just something you print out on a wall and hang up as a sign. It's a habit. It's what you do every day. I like this because this reframes our challenge, right? We accept failure. This is a good, smart approach, right? Things will go wrong in complex systems, so we should be able to accept that and learn from it. This is a smart, good idea. How do we make it part of our culture and not just a sign we put on the wall? Well, we reframe it. It's not how do we make this part of our culture, it's how do we make accepting failure a habit? How do we make accepting failure, learning from failure, something we do every day? Well, it's here, it's step 2. This is what we do in chaos engineering. Every day, every time we do chaos engineering, we induce failure. We create failure as an opportunity to learn. Chaos engineering, this loop here on the screen, literally turns learning from failure into a habit. I found another big sign that you can put on your wall. No one survives first contact with the enemy. This is misquoted by a few different people. I haven't ever quite been able to figure out who said it first. But I prefer Mike Tyson's formulation of this, which is that everyone has a plan until they get punched in the mouth. The idea here is good, though. Look, no matter how good your plan is, as soon as you start interacting with the system's going to start changing around you. No matter how good your plan is, it's going to need to change. It will not survive contact with the real world, with complex systems. Now, you could go on Etsy and buy this poster for €20 if you are so inclined. I'm not going to stop you, but I don't think hanging this up on your wall is going to change anything. How do you make understanding this, truly internalizing this approach, part of what you do? Part of what you do every day? Again, Netflix engineering principles. It's step 2. Step 2 is constantly questioning your assumptions. Did we get this plan right? Did our plan survive contact with reality? And yes, this was a sign that Netflix put up on their office walls, but they built a tool to do this. Chaos engineering, Chaos Monkey, all of these tools constantly show them that their plans don't always survive contact with reality. It helps them understand this. It turns it into a habit. Looking again at this loop here, I want to talk about chaos experiments for a bit. Because as I said, often when we introduce chaos engineering, we kind of frame it as, well, you just randomly turn off servers. You can do that. It can be fun, but there is a discipline that goes into this. So I want to kind of zoom in on this. And if you kind of dig into the literature around here, you will find a lot of work around chaos experiment design. How do you actually design one of these chaos experiments? Because again, it's not just, oh, we'll just turn some things off randomly. We need to think about this. We need to think about our target selection. What are we actually going to try to break? What are we going to try to bring down? Because as my friend Russ Miles puts it, if you take a service that you know is a single point of failure and you run a chaos experiment on it and it brings down your entire system, you haven't actually learned anything. You've just annoyed someone. You've just caused some downtime. That's not really an experiment. You've just annoyed someone. So we need to think carefully. Which of these experiments is going to cause us to learn the most about our system? It's going to identify potentially the biggest risks and the biggest weaknesses in our system. We need to think carefully about what we're targeting, not just picking things at random. And because these things will go wrong sometimes, we also need to think carefully about how we limit our blast radius. Things will go wrong. How do we stop it bringing down the entire business? You can do this in lots of different ways. You can do it by targeting just a small subset of your services. So, even in the worst case scenario, there's going to be limited damage, or maybe even starting with a non-production environment could be a good and smart way to go. You also need to think about having monitoring in place. If you break something, if you unleash the monkeys and you bring down a server, how do you know the impact that had? We need to be able to see what's going on inside our systems, monitoring and the bigger topic of observability. So when things do go badly wrong, we're able to really dig in and understand why. Again, if you just turn off a random server and walk away without looking at the results, that's not an experiment. You're not learning anything there. So we need to think carefully about how we learn. And we also need to think carefully about rollbacks, because things will go wrong and sometimes we're going to have to undo our damage. Now, we're quite lucky as software engineers. This can very often be automated. A previous team I worked with, we could reproduce our entire production environment in a few minutes with a Terraform config, which is great. That's great for recovering from disaster, from rolling back from disaster. But trust me, you don't want to be writing those Terraform config files while your business is burning down. So you should have these prepared ahead of time. And this is really what I mean here by discipline that goes into designing chaos experiments. Now, a couple of years ago, I was reading this article, The 7 Principles of Intervention in Complex Systems by Dave Snowden, who I mentioned earlier. And he's talking about how you approach changes in a complex system. He's a researcher in this field. And one of the first things is we need to treat these as experiments, because we're not sure if they're going to work. That's the nature of complex adaptive systems. We can't model and plan our way to the answer. They're experiments. We're not sure if they're going to work. So we need to think carefully about what experiments we're running. We need to do what's known as a coherence test. I can't say whether or not, if you come up with a hypothesis like, hey, if I do this, I think it's going to have the following impact, I can't tell you if you're right. But I can tell you, and I can answer whether or not it's coherent. Does it make sense? Does it match reality on at least some level? Again, we don't just want to be running any random experiment we think of. We also need to be thinking about how we make these experiments safe to fail, because some of these experiments will fail. In fact, if our experiments aren't failing, we probably aren't trying hard enough to push the envelope and really understand and explore the system. So how do we make these experiments safe to fail? We also need to think about having monitoring in place. How are we going to know if things are going badly wrong? And for that matter, how are we going to know if things are going well and we need to respond in a different way? We need to be building fast feedback loops so we can respond, if not in real time, at least fast enough to react meaningfully to what's going on in this system. And we also need to be thinking about a damping strategy. If I roll out a new strategy and it's not working, we need to slow it down. We need to pull energy away from that so it doesn't keep doing damage. The flip side of this is we also need an amplification strategy. If things are going well, how do I give it more energy? How do I allow more good things to happen? Now, if you're looking at those two lists and you're thinking, well, both chaos experiments and complex system experiments, well, they both need us to think very carefully about what we're actually doing. So we maximize our learning, we maximize our scanning and our exploration, and we're not just doing things randomly. In both of them, we need to think carefully about how we limit the damage we can possibly do. In both of them, we need to think carefully about how we monitor the impact of our experiments. And we also need to think about how we undo damage of our experiments if necessary. Now, if you're looking at these two lists and you're thinking, well, that's the same list, good job. You figured out the point of the talk, which is that a lot of the skills that you need to work with complex systems are some of the same skills that you build with chaos engineering. Embracing failure, embracing uncertainty, the discipline that needs to go into experiment design. These are skills that will serve you well in chaos engineering and working in complex systems, which realistically, the organization you're probably working in probably is. So there's other techniques as well when it comes to dealing with complex systems. I don't want to imply that chaos engineering will teach you everything. There's lots of other things you should be looking at. Constraint mapping is a powerful technique where we look at where we understand what the limitations of our systems are. Where can we and can't we act? Sense making, and I should put a hyphen there, otherwise Dave will get very angry. Sense making refers to understanding the world around us so that we can act in it. Very often our plans, we make 5-year plans, we make big roadmaps and big plans. And sense making instead says, no, let's look at where we are and figure out where we can go from here. Let's understand the as is, understand the evolutionary potential of the present, not just where we want to be in 5 years. Coherence testing we talked about, right? In complex systems, we can't model our way to the answer, but we can ask if our hypotheses are coherent. We also need to think about parallel probes, how we run multiple experiments in parallel, so we avoid effects like the Hawthorne effect and the Woozle effect, which I won't get into today, but feel free to look them up or message me afterwards. And there's also sidecasting. Sidecasting, which is a fantastic technique for looking at adjacent possibilities. Again, so many of our planning techniques involve looking at where we want to be rather than thinking about where we could be potentially soon or in an alternate timeline. There are fantastic techniques here, really important for dealing with complex systems. Chaos engineering doesn't teach you all of them, but I do think it's a pretty good first step. So when we look at this, when you look at chaos engineering, there's lots of stuff written about the chaos experiments, right? There's thousands of articles called Getting Started with Chaos Monkey, because everyone loves monkeys and Chaos Monkey is a funny word, right? And that's important. You need to be able to use these tools. You can do it you can just do it manually, actually. Like you don't need to start with the tooling, but there's some really, really useful stuff here. There's also some incredibly useful stuff written about how we learn from failure, which is an incredibly powerful technique that I think is very often underplayed in how we approach root cause analysis and incident analysis. But one of the main topics in the chaos engineering community is how we improve system resilience. Not just robustness, not just stop the failures, but stop the failures causing the bigger issues. How we adapt to and deal with those failures. I have a book on chaos engineering. I searched for the word resilience, and I found hundreds and hundreds of references to that one word. Resilience is a big topic in the chaos engineering space, the chaos engineering community, and it's an important one. But I also think that improving system resilience is a first order effect of chaos engineering. We do chaos engineering in order to improve system resilience. What this talk is about is the second order effects of chaos engineering. What other effects does that have beyond this, beyond that first order effect? How does it change our culture? How does it change how we think about our work, how we think about the world around us? That's where I think some of the real value in chaos engineering is. And for that matter, think about some of the other techniques that I'm sure you're all familiar with, or maybe even using. Test-driven design. You write your tests first before you write the functional code. We all know what the first order effect of that is, right? The first order effect of test-driven design is you have more tests. We love tests. That's great. Good news. What's the second order effect? How does it change how people think about their work? How does it change how people think about their roles, their responsibilities, about the development process, about everything? How does it change how people slice their work? What are the second order effects of these techniques? What about continuous integration, continuous delivery, continuous deployment, pairing? Again, easy to say what the first order effects are, but what are the second order effects? I'm at the end of the talk, so I will leave you with that little question. As I said, I don't think that chaos engineering is a silver bullet that is going to solve all of your problems. I don't think it's going to magically make you able to surf the complexities of complexity, but I do think it's a pretty good first step. Thanks. That's the end. I do have some references. Now would be a great time to take a screenshot. I will, I'll paste these into the chat in a sec as well. That's what I'll do. Yeah, but take a picture of these. There's there's the Cynefin article there. There's a couple of books. Edge, as I said, is good. Quite business focused, but I do think it's worth a read. Cynefin, Weaving Sense Making into the Fabric of Our World, is a great collection of essays on complexity in Cynefin, which is a related topic. Dynamics in Action is a very academic book on the dynamic systems and complex systems, but I'm a big fan of complexity and postmodernism. While it's a little bit academic, I think it's a fantastic, really, really fantastic analysis of what complex systems really mean. There's a short field guide here, looking at how to apply these sorts of techniques, particularly in the context of the recent COVID pandemic. And this is the Etsy debriefing facilitation guide, which is a fantastic look at how we learn from failures. So yes, take a screenshot and I will paste them in the chat in just a sec. Do we have any questions? Perhaps not. I have run this before and people have said that can be a bit, lots to take in. Hopefully that.
Hi guys, if you have any question, you can write into the chat or turn on your microphone and ask Steve your questions.
Yeah.
No? Okay, if nobody has questions, thank you a lot for your speech. I believe it was really valuable and really interesting for our audience today. Tomorrow, all of you guys, you will receive email with the recording of this webinar and with the materials that Steve shared with us. So thanks a lot for coming and see you next time on our events.
Yep. Thank you, Steve. Yeah, I saw your presentation during conference. Good job. Good information.
Thanks, folks. Have fun.
Okay. Bye. Have a nice evening.
Ciao, ciao.
All the best. Bye. Thank you.